Hello everyone, today we'll study arc length. How can we find the length of arc? In general, finding the length of arc of a function is not easy. But if the function is continuous and differentiable, then there's a way to find arc length using calculus. Next, let me show you this special case. Suppose function f is continuous and differentiable. On the interval from a to b. We try to find the arc length on function f from a to b. Find the arc length of function f on the interval from a to b. Next, let me draw a graph for function f. Suppose the graph of function f looks like this. Function f is continuous and differentiable from a to b. Which means the curve is connected and smooth between a and b. We try to find the length of arc from a to b, the length of this arc here. So, in order to find the arc length, let's first of all divide interval ab into n subintervals. Assume S1 is here, S2 is here, that's x3, continue. That's xi minus 1. That's xi. And the last piece is x sub m minus 1. B is xn. And a is x0. Here you can see that we divide interval ab into n subintervals. At the same time, I divide this arc into n pieces. Next, we try to find the length of arc for each pieces. In order to approximate the length of arc, we try to find the distance between the endpoints for each pieces. Find the distance between the endpoints for each pieces. Here you can see that as long as we make the interval small enough, the distance between the endpoints will be very, very close to the arc length. As long as we make each piece very, very small, the distance between the endpoints will be very, very close to the arc length. Now, how can we find the arc length? How can we find the distance between these two endpoints? How can we find the distance between these two endpoints? What's this point? What's this point? This point, the x-coordinate is x sub I minus 1. The y-coordinate is f of xi minus 1. That's this point. The x-coordinate and the y-coordinate. How about this point? What's an x-coordinate? What's an y-coordinate? For this point, the x-coordinate is x sub I. And the y-coordinate is f of si. That's these 2 points. Now, how can we find distance between 2 points? We know that, in general, for distance between 2 points, the formula is x2 minus s1 squared plus y2 minus y1 squared. That's the distance between 2 points. Let me apply here. Find distance between these 2 points. So distance between these 2 points is square root of S2 minus S1. Let's call this point S1, Y1. Call this point S2, Y2. So S2 minus S1 will be Si minus Xi minus 1 squared. That's S2 minus S1 plus Y2 minus Y1, which is f of Si minus f of Si minus 1 squared. That's the distance between these 2 points. That's how we find the distance between these 2 points. Now, next, how can we simplify this expression? How can we simplify this expression? In order to simplify this expression, let me first of all remind you the mean value theorem. The mean value theorem says, suppose f is continuous on a closed interval AB and differentiable on an open interval AB, then there exists a real number C between A and B such that f prime of C equal to f of B minus f of A over B minus A. Or equivalently, this formula can be rewritten as f of B minus f of A equal to f prime of C times B minus A. Now here, in this function f, on the interval from xi minus 1 to si, we can see that function f is continuous and differentiable. So, since f is continuous and differentiable, on the interval from xi minus 1 to si, then by the mean value theorem, there exists a constant called C. Since this constant C is in the I subinterval, let me call this constant Ci. Since C is in the I subinterval, let me call this constant Ci. There exists a constant Ci in the interval from xi minus 1 to si, such that by mean value theorem, f of xi minus f of I minus 1 equal to f prime of C, f prime of Ci times Si minus Xi minus 1. By mean value theorem, we have f of Si minus 1, f of Si minus f of Si minus 1 equal to f prime of Ci times Xi minus Si minus 1. So d, the distance can be rewritten as Si minus Si minus 1 squared plus f of Si minus f of Si minus 1 squared. Here in the parentheses, f of Si minus f of Si minus 1, that can be rewritten as f prime of Ci times Si minus Si minus 1. Square. Next, what's Si minus Si minus 1? Si minus Si minus 1, that's the distance between these 2 points. That's delta Si. Si minus Si minus 1, that's the distance between these 2 points. That's delta Si. So Si minus Si minus 1, that's delta Si. So that's delta Si square plus, if I distribute square, I get f prime of Ci square times si minus si minus 1, that's delta x. Si minus si minus 1 is delta x. That's delta x, delta si. Si minus si minus 1, that's delta si. Distribute square, so I get square here. Next, let me copy everything over. The distance is square root of delta si square plus f prime of ci square times delta si square. Next, I can factor. We can see that here delta si is a common factor. If I factor pull out delta si, what do we get? If I factor pull out delta si square, I get 1 plus f prime of ci square. Then since delta si is always positive, square cancel square root, I get delta si times square root of 1 plus f prime of ci square. Since delta si is always positive, square cancel square root, I get d equal to delta si times square root of 1 plus f prime of ci square. That's the distance of this piece. That's the distance between these two endpoints. That's very, very close to the arc length of these pieces, of this piece. Next, for the total arc length, I find the sum for I from 1 to n. From total arc length, I take the sum. So for the approximate arc length, for an approximate total arc length, I take the sum for I from 1 to n. That's an approximate arc length. The distance between the endpoints is very, very close to the arc length, but it's not the exact arc length. Distance between the endpoints is very, very close to the arc length, but it's not the exact arc length. So that's an approximate total arc length. I have to take the sum I from 1 to n. Take delta si times square root of 1 plus f prime of ci square. And since ci is a point, between the subintervals from si minus 1 to si, I can choose the sample point to be ci. Note, since ci is between xi minus 1 si for all I from 1 to n, then we can choose the sample point to be ci. Choose the sample point si star equal to ci for each subinterval. So the approximate arc length can be written as the sum I from 1 to n delta si times square root of 1 plus f prime of si star square. that can be rewritten as the sum I from 1 to n. Let me put delta Si to the back. 1 plus f prime of Si star square times delta Si. That's an approximate arc length. For the actual arc length, we must take limit. That's an approximate arc length. For the actual arc length, we must take limit. Take limit as the maximum delta Si approach to 0. If the maximum delta Si approach to 0, that means each subinterval will be very, very, very small. Every subinterval will be very, very small. So the approximate arc length will be very, very close to the actual arc length. That's how we find the actual arc length. So take limit as the maximum delta Si approach to 0. That's the actual arc length. And here we can see that this is a Riemann sum. This is a Riemann sum. Then, by the definition of definite integral, this limit can be written as integral from a to b square root of 1 plus f prime of x square. Delta Si become dx. By definition of definite integral, this limit can be noted as integral from a to b square root of 1 plus f prime of x square dx. That's the actual arc length. And also, in general, we can write f prime of x as dy over dx. If I treat y as f of x, f prime of x can be rewritten as dy over dx. Square times dx. That's the length of arc from A to B. That's the length of arc from A to B on function f. Similarly, if x equal to g of y is continuous and differentiable, if I write x as a function of y, if this function is continuous and differentiable, on the interval from C to D, then the length of arc can be written as integral from C to D square root of 1 plus, if x is a function of y, the derivative can be written as dx over dy square times dy. So when y is a function of x, we use this formula. When x is a function of y, I use this formula. Keep these two formulas in mind. When y is a function of x, use this formula for arc length. And when x is a function of y, use this formula for arc length. Next, let me show you some examples. Let y equal to x squared. Find the length of an arc of the interval from -1 to 2. So here, y is a function of x. The arc length formula is integral from a to b, square root of 1 plus dy over dx squared dx. Since y is a function of x, the formula is integral from a to b, square root of 1 plus dy over dx squared times dx. What's dy over dx? Here, y is x squared. dy over dx is 2x. So we plug in 2x for dy over dx. Here, a and b is -1 and 2. So the integral from -1 to 2. Square root of 1 plus 2x squared dx. That's 1 plus 4x squared. In this section, all integrals involve square roots. Solving integrals with square roots may be too complicated. So for this section, for all arc length, I will solve integrals using calculator. So for this integral, using calculator, I get 6.1257. For this section, we will solve integrals using calculator and round the answer to 4 decimal places. Next example. Let y equal to cosine of x. Find the length of an arc. On the interval from 0 to pi over 2. So here, y is a function of x. For the arc length, I use the formula integral from a to b, square root of 1 plus dy over dx squared times dx. In order to find the arc length, first step, find dy over dx. Here, y is cosine of x. So dy over dx, derivative of cosine is negative sign. Then plug in. Here, a is 0, b is pi over 2. So I take integral from 0 to pi over 2. Square root of 1 plus negative sine x squared times dx. If we simplify, we get 1 plus sine square x dx. Next, I use my calculator to solve this integral. In my calculator, I get 1.9101. Round the answer to 4 decimal places. Next example. Let s equal to y cubed plus 2. Find the length of an arc. On the interval from 0 to 2. So here we have x as a function of y. So for the arc length, use the formula integral from c to d, square root of 1 plus dx over dy squared times dy. Since x is a function of y, we are doing dy. The derivative here is dx over dy. We have x equal to y cubed plus 2. What's dx over dy? For dx over dy, we take derivative. I get 3y squared. Then plug in. Here, interval is from 0 to 2, so that's our c and d. Take integral from 0 to 2. Square root of 1 plus dx over dy is 3y squared. That's 1 plus 9y to the power 4 dy. Next, use calculator for integral. In my calculator, round the answer to 4 decimal places. I get 8.6303 03. Next example. Let s equal to y times e to the power of y. Find the length of an arc on the interval from -1 to 1. Here, x is a function of y. So for the arc length, using the formula, integral from c to d, square root of 1 plus dx over dy squared, since x is a function of y. First step, let's find dx over dy. Since x is y times e to the power of y, how can we find dx over dy here? Here, for dx over dy, we must use product rule. Use product rule. Derivative of the first times the second plus the first times derivative of the second. Then simplify. It can be rewritten as e to the power of y times 1 plus y. I can factor e to the power of y out. I get 1 plus y in the parentheses. Then plug in. Here c and d is -1 and 1. So take integral from -1 to 1. 1 plus square root of 1 plus dy over dx. That's e to the power of y times 1 plus y square dy. If we simplify, we get square root of 1 plus e to the power of 2y times 1 plus y square dy. Then use calculator for integral. In my calculator, I get 4.0293. Next example. Find the perimeter of the region bounded by curves y equal to x squared and y equal to 2 plus x. How can we find the perimeter of the region here? In order to find the perimeter of the region, let's graph the region first. The region is bounded by these two curves, y equal to x squared and y equal to 2 plus x. Let's graph both curves first. First curve, y equal to x squared. It's a parabola open upward. That's the curve, y equal to x squared. Second curve is y equal to 2 plus x. That's a straight line. Slope is 1, y-intercept is 2. That's a straight line. Slope is 1, y-intercept is 2. That's the second curve, y equal to 2 plus x. That's the region bounded by both curves. That's the region bounded by both curves. So for the perimeter, we must find the arc, the length of this arc, plus the length of this arc. That's the perimeter of the region. Assume the length of this arc is L1. The length of this arc is L2. The perimeter of this region is L1 plus L2. That's the perimeter. Now, how can we find L1? L1 is the arc length of this function, y equal to 2 plus x. For this function, y equal to 2 plus x, dy over dx, when we take derivative, dy over dx is 1. So for L1, we have integral from a to b, square root of 1 plus dy over dx squared times dx. That's L1. We'll do L2 later. That's L1. We'll do L2 later. dy over dx is 1. But what's a and b here? What's a and b here? Here, a and b are the intersection of these two curves. A and b are the intersection of these two curves. So in order to find A and B, let's find the intersection between the two curves. So for intersection, I set x squared equal to 2 plus x. Bring 2 and x over. I get x squared minus x minus 2 equals 0. Factor, I get s minus 2 times s plus 1 equal to 0. Solve an equation, s is 2 and s is negative 1. So the smaller number is a, larger number is b. So take integral from negative 1 to 2. Square root of 1 plus the derivative dy over dx is 1. dx. We'll do L2 later. That's L1. If we simplify, we get integral from negative 1 to 2. Square root of 2 dx. That's L1. Next, let's find L2. L2 is the length of this arc. This curve is y equal to s squared. Since y is a function of x, for the arc length, I use the formula integral from a to b. Square root of 1 plus dy over dx squared dx. Here, for the second function, y is s squared. If I take derivative, dy over dx is 2x. Plug in here. Plug in 2x for dy over dx. Here, take integral from a to b. A and b are the intersections of these two curves. So they are negative 1 and 2. 1 plus dy over dx squared. dy over dx is 2x. Simplify is the integral from negative 1 to 2. Square root of 1 plus 4x squared dx. Next, we use calculator for integrals. In my calculator, I get 4.2426 for the first integral. And I get 6.1257 for the second integral. Adding up, I get 10.3683. That's a perimeter of this region. That's a perimeter of this region. Next example. Find the perimeter of the region bounded by curves y equal to square root of x, y equal to e to the power of x, s equal to 0, and s equal to 4. Find the perimeter of the region bounded by these 4 curves. So in order to find the perimeter, let's graph the region first. First curve is y equal to square root of x. It's y equal to square root of x. Second curve is y equal to e to the power of x. That's the second curve, y equal to e to the power of x. Third curve is s equal to 0. S equal to 0 is the y-axis. S equal to 0 is the y-axis. Next curve is s equal to 4. S equal to 4 is a vertical line. They're passing through 4 in the s-axis. S equal to 4 is a vertical line passing through 4 in the s-axis. So that's the region bounded by these 4 curves. That's the region bounded by these 4 curves. Now, How can we find the perimeter here? For this region here, it has 4 boundaries. 1, 2, 3, 4. Assume the arc length of this piece is L1. Arc length of this piece is L2. Arc length of this piece is L3. And arc length of this piece is L4. The perimeter of this region is L1 plus L2 plus L3 plus L4. Let's find L1, L2, L3, L4 individually. So here let's find L1 first. L1 is the arc length of this function, y equal to e to the power of x. Here, y is a function of x. So the arc length formula is integral from a to b, square root of 1 plus dy over dx squared times dx. For L1, y is e to the power of x. If I take derivative, dy over dx, it stays the same. It's also e to the power of x. Then plug in. Integral from a to b for L1. L1 is bounded by 0 and 4. So that's a, that's b. So integral from 0 to 4, square root of 1 plus dy over dx squared. Here, dy over dx is e to the power of x times dx. That can be rewrite as integral from 0 to 4, square root of 1 plus e to the power of 2x dx. That's L1. How about L2? L2 is the arc length of this function, s equal to 4. Here, for s equal to 4, we treat x as a function of y. So the arc length formula is integral from c to d, square root of 1 plus dx over dy squared times dy. For this function here, x is 4. This is a constant function. If I take derivative, find dx over dy. Derivative of constant is 0. So dx over dy is 0. What's c and d here? What's c and d here? This point here is c. This is d. Integral from c to d. Lower bound is c. Upper bound is d. How can we find c and d here? So for c here, I plug in 4 into this function. Plugging 4 into this function, I get y equal to square root of 4, which is 2. Here for c, I plug in 4 into this function. I get y equal to square root of 4, which is 2. So c is 2. How about d? D is this point. I plug 4 into this function. I get e to the power of 4. Plug 4 into this function. I get e to the power of 4. That's d. Square root of 1 plus dx over dy squared. Dx over dy is 0. Times dy. I get integral from 2 to e to the power of 4 times square root of 1. Square root of 1 is 1 dy. That's L2. How about L3? L3 is the length of this arc. This function is y equal to square root of x. Here, y is a function of x. So use the formula integral from a to b, square root of 1 plus dy over dx squared times dx. Here, since y is square root of x, what's dy over dx? Dy over dx can be rewrite as, if I take derivative, square root of x is x raised to a half. If I take derivative, that's 1 over 2 times x raised to negative half. That can be rewrite as 1 over 2 square root of x. That's dy over dx. Then plug in. What's a and b here? For L3, this arc is bounded by 0 and 4. So that's A, that's B. dy over dx is 1 over 2 square root of x, then square times dx. If we simplify, we get 1 plus 1 over 4x dx. That's L3. How about L4? L4 is the length of this arc. This curve here is s equal to 0. Here we can treat x as a function of y. Since I treat x as a function of y, take integral from c to d. Square root of 1 plus dx over dy squared times dy. What's c and d? C is the origin. That's 0. How about D? D is this point. That's C, that's D. D is this point. For this point, we plug 0 into this function. If we plug in 0 here, e to the power of 0 is 1. So C is 0. D is e to the power of 0, which is 1. So take integral from 0 to 1. Square root of 1 plus dx over dy. What's dx over dy? For this curve here, s is 0. The function is s equal to 0. If I take derivative, dx over dy, derivative of 0 is 0. Derivative of 0 is 0. We get 1 plus 0 squared times dy. Let's integral from 0 to 1 times 1 dy. Then we can solve each integral using calculator, then add them up. For the perimeter, we use L1 plus L2 plus L3 plus L4. Next, I'll use calculator to solve each integrals, then add them up. In my calculator, L1 is 54.0562. L2 is 52.5982. L3 is 4.6468. L4 is 1. Then add them up. Take L1 plus L2 plus L3 plus L4. In my calculator, I get 112.3012. That's the perimeter of this region. That's the perimeter of this region. Next example. Find the perimeter of the region bounded by curves s equal to y squared minus 4 and s equal to 2y minus y squared. For this example, in order to find the perimeter of the region bounded by these two curves, let's graph the region first. First curve is s equal to y squared minus 4. Since y squared is positive, that's a parabola open to the right. That's a parabola open to the right. And here, if I set s equal to 0, the y-intercept is positive negative 2. If I set s equal to 0, the y-intercept is positive negative 2. And that's a parabola open to the right. So that's the graph of s equal to y squared minus 4. Next curve, s equal to 2y minus y squared. Since y squared is negative, that's a parabola open to the left. If I say s equal to 0, the y-intercept is 0 and 2. That's a parabola open to the left, and the y-intercept is 0 and 2. The graph looks like this. That's a region bounded by the curves. We're looking for the perimeter. So here, the perimeter will involve two pieces. This piece and this piece. Assume the arc length of this piece is L1, and the arc length of this piece is L2. The perimeter of this region is L1 plus L2. Let's find L1, L2 individually, and then add them up. Let's find L1 first. L1 is the arc length of this curve, s equal to y squared minus 4. For this curve, we have x in terms of y. So the arc length is integral from c to d, square root of 1 plus dx over dy squared times dy, since we have x in terms of y. That's L1. We'll find L2 later. This is L1. Here, what's C and D? For L1, that's the lower bound, and that's the upper bound. That's the intersection of these two curves. These 2 points, they are the intersection of these two curves. So I set these two curves equal to each other. We get y squared minus 4 equal to 2y minus y squared. Let's first of all move everything to the left side. We get 2y squared minus 2y minus 4 equal to 0. If I divide both sides by 2, I get y squared minus y minus 2 equal to 0. If I factor, I get y minus 2 times y plus 1 equal to 0. Solve the equation, y is positive 2 and y is negative 1. So that's the lower bound, that's the upper bound. Lower bound is negative 1, upper bound is 2. So take the go from negative 1 to 2. Square root of 1 plus dy over dx squared. What's dy over dx? L1 is the arc length of this function, s equal to y squared minus 4. If I take derivative, dx over dy is 2y. If I take derivative, dx over dy is 2y. So plug in 2y here. Let's integral from negative 1 to 1. Square root of 1 plus, so integral from negative 1 to 2. Square root of 1 plus 4y squared dy. That's L1. Next, let's find L2. L2 is the arc length of this function, s equal to 2y minus y squared. Since we have x in terms of y, use the formula integral from c to d, square root of 1 plus dx over dy squared times dy. Here, what's c and d? For L2, that's the lower bound, that's the upper bound. So lower bound is negative 1, upper bound is 2, times square root of 1 plus dy over dx squared. Sorry, dx over dy squared. What's dx over dy here? For the second curve, s is 2y minus y squared. If I take derivative, then dx over dy will be 2 minus 2y. Plugging, we have 2 minus 2y squared times dy. Simplify. What's 2 minus 2y squared? If we spend a perfect square, 2 minus 2y squared is 4 minus 8y plus 4y squared. When we combine like terms, let's integral from negative 1 to 2. 1 plus 4 is 5. That's 5 minus 8y plus 4y squared times dy. Then use calculator for both integrals. In my calculator, I get 6.1258 for both integrals. Then add them up, I get 12.2516. That's the perimeter of this region. Next example. Find the perimeter of the region. Bounded by curves x times y equal to 4, y equal to x, and y equal to x plus 3. In order to find the perimeter of this region, let's graph this region first. First curve is x times y equal to 4. X times y equal to 4. This equation can be rewritten as y equal to 4 over x. This equation, x times y equal to 4, it can be rewritten as y equal to 4 over x. Let's graph the region first. First curve, y equal to 4 over x. This is a hyperbola. This graph looks like this. Y equal to 4 over x. It's a hyperbola. There are two pieces. Second curve is y equal to x. That's a straight line. Y-intercept is 0. Slope is 1. And the first curve is y equal to 4 over x. Second curve is y equal to x. The third curve is y equal to x plus 3. That's a straight line. That's a straight line. Slope is 1. Y-intercept is 3. That's the third curve. Y equal to x plus 3. That's the region bounded by these four curves. That's the region bounded by these four curves. For the perimeter, we must calculate the arc length for these four pieces. 1, 2, 3, 4. For the perimeter, we must calculate the arc length for these four pieces. 1, 2, 3, 4. Assume the arc length of this piece is L1. Arc length of this piece is L2. Arc length of this piece is L3. And arc length of this piece is L4. The perimeter is L1 plus L2 plus L3 plus L4. Let's find each one individually. Let's find L1 first. L1 is the arc length of this curve. For this curve, we have y in terms of x. So take integral from a to b. Square root of 1 plus dy over dx squared times dx. That's L1. What's a and b here? A and b is the intersection between this curve, y equal to x plus 3 and y equal to 4 over x. So for a and b, I set x plus 3 equal to 4 over x. Solve an equation for x. If I multiply both sides by x, I get x squared plus 3x equal to 4. That can be rewritten as x squared plus 3x minus 4 equal to 0. If I factor, I get x plus 4 times x minus 1 equal to 0. Solve an equation. S is negative 4 and s is positive 1. So that's an upper bound and lower bound. From negative 4 to 1, integral of 1 plus dy over dx squared. What's dy over dx? L1 is the arc length of this curve, y equal to x plus 3. If y is x plus 3, when I take derivative, dy over dx is 1. Then plug in. One plus 1 is 2. We can use calculator for integral. We'll do it later. Next, let's find the arc length for L2. Let's find L2. L2 is the arc length of this function, y equal to 4 over x. Since we have y in terms of x, for L2, since we have y in terms of x, we use the formula integral from a to b, square root of 1 plus dy over dx squared times dx. First step, let's find a and b. What's the limit? What's a and b here? Here, a and b is the intersection between these three curves. That's a, that's b. Point A, that's the intersection between x plus 3 and 4 over x. And this value is positive. We set x plus 3 equal to 4 over x. Solve the equation. The positive solution is s equal to 1. So that's A. S is 1. So A equal to 1. How about B? B is the intersection between y equal to x and y equal to 4 over x. Let's set these two equations equal to each other. If I set s equal to 4 over x and solve the equation, I can first of all multiply both sides by x. I get s squared equal to 4, which means s equal to plus or minus 2. S equal to positive 2 or negative 2. Since this number here is positive, this x is positive, so we use s equal to 2. So x is from a is from 1 to 2. A is 1, b is 2. S is from 1 to 2. Square root of 1 plus dy over dx. L2 is the arc length of this curve, the hyperbola, y equal to 4 over x. If y is 4 over x, that can be rewritten as 4 times x raised to negative 1. If I take derivative, dy over dx is negative 4 times x raised to negative 2. That can be rewritten as negative 4 over s squared. That's dy over dx. Plug in. We have negative 4 over s squared times dx. If we simplify, we have square root of 1 plus 16 over x to the power 4 dx. We can solve it using calculator. We'll do it later. That's L2. Next, let's find L3. L3 is an arc length of this curve, y to x. That's L3. Since we have y in terms of x, we use the formula integral from a to b, square root of 1 plus dy over dx squared dx. L3 is the arc length of the function y equal to x. So dy over dx is 1. dy over dx is 1. How about upper and lower bound? What's a and b here? For L3, that's a lower bound, that's an upper bound. So for L3, I set the equation y equal to x equal to the equation 4 over x. I set s equal to 4 over x. Solve the equation and get s equal to positive 2 and s equal to negative 2. So that's negative 2, that's positive 2. That's a lower bound, that's an upper bound. So for L3, take integral from negative 2 to positive 2. Square root of 1 plus dy over dx. Here, dy over dx is 1. Square root of 1 plus 1 is square root of 2. We can solve it using calculator. We'll solve it later. We can solve integral using calculator. We'll solve it later. Next, let's find L4. What's L4? L4 is an R-line of this curve. This curve is y equal to 4 over x. Since we have y in terms of x, we use the formula integral from a to b, square root of 1 plus dy over dx squared dx. L4 is the R-line of this curve, y equal to 4 over x. When y equal to 4 over x, when I take derivative dy over dx, I get the same answer here. I get negative 4 over s squared. Let's dy over dx. What's a and b here? What's a and b here? For L4, that's the intersection. That's a, that's b. Those are the boundaries. That's a, that's b. Here, this point is the intersection between the hyperbola y equal to 4 over x and this line y equal to x plus 3. So I set, for this point, I set x plus 3 equal to 4 over x. Solve the equation, we get two solutions, x equal to negative 4 and x equal to positive 1. We know that this point here is negative, so we use negative 4. So that's a lower bound, negative 4. Lower bound is negative 4. How about the upper bound? Upper bound is this point. This point is the intersection between the hyperbola and the straight line y equal to x. So set x equal to 4 over x. I can find this point. Set x equal to 4 over x. I get two solutions, x equal to positive 2 and x equal to negative 2. We know that this point here is negative, so we use negative 2 here. So upper bound is negative 2. That's the lower bound, that's upper bound. Upper bound is negative 2. Square root of 1 plus dy over dx squared. Here, dy over dx is negative 4 over s squared. Square times dx. If we simplify, what we have under square root is 1 plus 16 over x to the power 4 times dx. Next, we use calculator to solve each integrals. Use calculator to solve each integrals. In my calculator, the first integral is 7.0711. The second integral is 2.2642. The third integral is 5.6569. And the fourth integral is 2.2642. Then for the perimeter, we use L1 plus L2 plus L3 plus L4. Adding up, here L1 is 7.0711. L2 is 2.2642. L3 is 5.6569. L4 is 2.2642. Adding up, in my calculator, I get 17.2564. That's the arc length. That's the perimeter of this region. That's the perimeter of this region.